Okay. Well, welcome everybody. This is our first webinar in our new webinar series on computational social science. We would very much appreciate getting feedback on them. We want to know what you like, what you don't like, the format, topics you'd like to hear about, and of course, if you'd like to present a webinar as part of the series, please let us know. And so all feedback, just send to board@computationalsocialscience.org. And again, anything is fair game. Let us know. Goods, bads, uglies, all that jazz. So this first webinar of ours is going to be a discussion about applied computational social science. And for better or worse, you're going to hear it from me. And then, again, this is an interactive webinar, so please type questions into the chat. Of course, if you're watching this as a recording, that won't be quite as useful as it would have been when it was live. Feel free to type comments into the video, of course, but don't expect an immediate response. Okay, so I should also say that my affiliation with MITRE is strictly for information purposes only, and this shouldn't be seen as an official statement by MITRE itself. So, what are we going to cover here? First, I'm going to tell you a little bit more about myself so you understand all of the biases and mental hiccups that I bring to the party. Then we're going to talk a little bit about computational social science and arguably complex adaptive systems, and then a potential path through basically the mess of trying to make sense of social systems and why that's hard and what tools are now available to try to make sense of all this. And again, we want this to be an informal sort of webinar. We want this to be of value to the society, so please do put questions in the chat. We are monitoring it, and we'll do our best to get everything answered. Okay, moving on. So I am a social scientist that came to computation, and the reason I bring that up is just to make sure that you understand that I'm coming at this from a social science theory perspective, and I'm not a great coder. So the computational stuff I come up with isn't particularly elegant, but it's trying to do a good job of representing the theory of how humans work rather than elegant algorithms. My background, I have degrees in anthropology, public affairs, law, and computational social science. Conspicuous by its absence is anything from computer science in there. Having said that, I really like agent-based models. As far as I'm concerned, everything should be an agent-based model, and we'll talk a little bit more about that in a few slides. And I don't come at this from academia. I work for the MITRE Corporation, which is a not-for-profit that operates 7 federally funded research and development centers. And again, to beat this drum, my affiliation with MITRE, and I bring that up again just for informational purposes and not to try to imply that MITRE or the federal government is making an official statement here. But the reason I think it's useful to bring MITRE up is because it's an FFRDC, it's filling a role between the foundational science going on in academia and the applied science that the federal government needs to help it deal with some of its hard problems. And so I think that positions MITRE perfectly to do applied computational social science. And I'm lucky enough to be part of that at MITRE, and I really very much enjoy it. And so because I'm coming at this from an FFRDC perspective, it is a little bit unique. I don't work for a for-profit where we're trying to make money, trying to be efficient, but I'm also not in academia where I'm doing foundational research. I'm in this sort of curious region in the middle where I'm trying to apply the foundational science going on in academia to the problems that's facing the federal government. All right, now let's get into some of the nitty-gritty here. So first and foremost, we do need to make a distinction between complicated and complex because it's important to get there. One of my favorite all-time pictures is at the top right here, this explosion of color here. And it's a little bit hard to tell with this resolution, but that's actually a traffic jam of kayaks in Southeast Asia. And I just find that to be immensely entertaining to look at. So let's talk a little bit more about complicated versus complex systems. So we've got this unhappy Lexus here, then disassembled, laid out fairly logically, and it is really complicated. There are a lot of parts to a Lexus, it turns out. And that's not even fully disassembled. But it's all physics. It's linear. It's been engineered, and we understand how everything works. It's repeatable. And the suspension system does what a suspension system does, whether it's connected to the car or not. The spring will still compress and then release, whether it's been bolted together or it hasn't. Linear, and it's extremely predictable. So while that is a very complicated system, it is not a complex system. Now, if we put it together and add a human to the mix, now do we have a complicated or a complex system? One car on the highway, at that scale, probably just complicated. Now, the human itself, of course, is a complex system. We've got, our immune system. We've got our gut biome. We've got all kinds of crazy stuff going on within the human. The neurons, consciousness, all that jazz. But the human-car combo is probably still complicated at this point. Now, what happens if we get a whole bunch of humans behind the wheel? Now we definitely have a complex system. Now, why do we say that? Well, that's because now there's interaction among the components. When it was a single person on the highway, there was no interaction. Now we've got multiple people, and they're interacting. There's feedback. What I do impacts someone else. What they do can impact me. And we can get emergent phenomena. We can get macroscopic dynamics that are hard to infer from the components. So, for example, here we can see that traffic jams and traffic. Now, what's actually about traffic jams is that the jam, the people having to slow down for a while in an area, that maintains, that dynamic stays put while the cars are continuing to turn over within the jam. The jam doesn't involve the same cars over time, yet the traffic jam itself stays there. The traffic jam also propagates against the flow of traffic. And these are both these are both characteristics of a traffic jam. They're difficult to infer from a detailed study of a car. Because of that, we can call this a complex system. So we talked about humans in a complex system, but is that unique to humans? And unfortunately, it isn't. So even if you don't study humans, you're still not off the hook when it comes to complexity. Ants, for example, a single ant, pick them up, try to have a chat, not going to have much to say. Ants are just not that bright. Very limited memory, very limited, computing capabilities on board. You put them in a novel environment, mostly they die. But if you get enough of them together, now suddenly you have an ant colony. And the ant colony can farm, can go to war, can find optimal foraging paths, can build structures. All of these things that are very difficult to infer from a detailed study of an ant. Even, all the molecules in that little critter. Still difficult to say that enough of them together and you get a colony. Okay, so eusocial insects, what if I don't care about eusocial insects? No, unfortunately, you're still not off the hook when it comes to complexity. Say water molecules even. Wetness is an emergent property of water molecules. It takes more than one water molecule to produce wetness. And even grain doesn't get you off the hook. One of the canonical examples in this space from Bach et al. is the self-organized criticality, and one of the sort of the examples of that is the sand pile and the avalanches from sand piles. It turns out it works a little bit better with medium-grain brown rice, but you still end up with a complex system, even with something completely inanimate that just lays there, like rice and like sand. Forest fires, earthquakes, all that jazz. Complexity is ubiquitous in these various systems. It doesn't require humans, it doesn't require eusocial insects. It requires components that somehow interact and can produce dynamics that are different at different scales. And where inferring the dynamics, understanding the dynamics at one scale doesn't really help you infer the characteristics and dynamics at another scale. So, we've talked about some examples. Can we now define a complex system? That's actually a little bit difficult, not totally recurring, a completely agreed upon example here. But on the whole, as we've said before, there are many parts, these parts interact, there's heterogeneity, and that heterogeneity is very broad, meaning that the components can be different, or the components can all be the same, but they have different experiences, they're in different places, they have different information, they have different neighbors. So the heterogeneity can come from what the component is or how the component has existed through time and space. These macroscopic structures, it has macroscopic structures and emergent phenomena, like cars, and you get enough of them together, you have a traffic jam. And there's the potential for adaptation and learning. And that's, largely when we involve, say, humans or other species that can learn and adapt. But again, as we've discussed, right, water molecules don't learn and adapt, rice grains don't learn and adapt, so that's not a critical component for complexity. It certainly helps, but it's not necessary. And so, trying to find, and again, there's this gray area, right? One car with a human behind it. Is it complicated or complex? So at that point, it's the scale of your analysis. The human itself is complex. The human driving a car by themselves on a highway is not. And so that finding the distinction between complicated and complex will be very contextual, but it's an important question to answer, because if you're dealing with a complicated system, we have lots of great tools. Optimization is a nice, crisply definable thing in most cases. When it's complicated, you can do a lot of fancy stuff there. And decision-making can be quite a bit simpler. That's not necessarily the case with complex systems. And now what we're going to do is talk a bit more about how all that works. How do we deal with the complex system when we're no longer in the complicated realm? And also, of course, from a computational social science perspective, because that's why we're here. That's what we're passionate about. So again, humans make complex systems. It's pretty easy for them to get to that state. And so that's why we're stressing complex systems a bit here, because while it's computational social science, in almost every case we're going to end up butting up against a complex system. So those dynamics can be a little bit difficult to deal with. And so we need to be cognizant as computational social scientists of how to deal with complexity. So computational social science has been enabled by staggering quantities of newly available micro-level data, like cell phone use, social media, transaction data, the ability to monitor traffic, trades in financial markets, other gigantic, crazy digitized data sets recently. Like if anyone has run across the Old Bailey data, Old Bailey is a court in London, and they've recently digitized and OCR'd roughly 300 years worth of transcripts from court cases that they've heard, which is just extraordinary. And of course, with all this data, we need big iron and big software to deal with all of it and process it correctly and do something useful. So what is CSS? Like complexity, so we've talked a little bit about, its social systems, its big data and things like that. Again, people can debate about what CSS actually is. In my view, computational social science is simply the non-trivial use of computation to analyze, visualize, and explore social dynamics. Meaning it's not using a word processor to write a report about a social system. It's doing something non-trivial to analyze the data coming from that system, or to visualize it and or to model it. So it's more than just a cool database or writing a paper. You need to be crunching numbers and making models. Now, one thing we certainly don't want to imply here is that computational social science is simply big data. I think there's a lot of value to be gained from the careful analysis of gigantic data sets, but computational social science, in my view, is often the combination of big data and big theory. And I say that with all due respect to Jeff West. He was the first person I heard articulate that. And that's particularly true when there are perturbations. And so, in my day job, like I said earlier, I do a lot of work with the federal government, and typically the federal government is trying to understand how to change a system, how to make it do something different, how to make it better. And so, we can get a ton of data about that system, and we can use all kinds of cool machine learning and artificial intelligence techniques to find lots of interesting correlative structures in it. But now we want to change it. We want to perturb it. We want to make some sort of difference there. Now we've changed the generating mechanisms, and now we're out of sample. And so now all these interesting insights and all these structures that we found in the data that the system had been producing, well, now it's a little tricky. How much space do we put in those sorts of things? This is where you need big theory, because with the theory about how these systems work, you can now put models together and start to understand how, when they're perturbed, they may react. And so you may get a better sense of how to actually make a perturbation to cause a particular change. And that's something that I would argue can't be done if it's simply a big data-driven system, big data-driven analysis. Okay, so now we're going to spend a few more minutes to just dive in and start talking about how to actually do this, because there's been a lot of hand-waving at this point, quite honestly, and it doesn't need to be. And I don't want to give anyone the impression that this is simply, an art. This actually is a science. So, first off, there is a ton of solid science that underlies complex systems in social science. We've got hundreds and hundreds of years worth of economic analysis, of sociocultural analysis, of psychology, and cognitive science. We understand an awful lot about humans, and we understand an awful lot about how to express the dynamics of a complex system. There's a ton of science out there. It's difficult to wade through for sure, but it's there, and we should build on it. We want this to be a repeatable science. And as I said a couple of slides ago, learn to love the theory. The theory helps understand where to draw the box so that you can, you're building models, you're doing analyses, you can't boil the entire ocean, so to speak. You have to exclude things from your analysis. You have to exclude, characteristics of the system from your model. And with a good understanding of the theory, that'll help you draw those lines in very principled ways. And again, as I said before, and I'm going to foot stomp this because I think it's very important, it also helps with the out-of-sample issues. With good theory, you can start to build the generative analyses that you need to understand how the system might work when it's in a state that you don't have data for. The details matter, but almost no one cares. And I think this is very, very important. Again, building on all that science and building on principled analytic techniques, you can build defensible, repeatable, transparent analyses of these incredibly complicated and complex systems. And doing so allows you to defend your work and will allow your work to have more of an impact. Now, it's unbelievably painful to actually do this. And for the most part, no one's going to hold your feet to the fire but you to actually, go through it all. It's really painful to do sometimes. To have a formulation that's very detailed, to go through the literature and do a thorough lit review, and then start to build things up and defend the decisions that you've made and express all of your assumptions in a clearly articulated way so that those that come next can repeat your work and then build on it. That's painful, but it's important. And especially, in my space, doing this as an applied science for the federal government, there's a ton of oversight that it can be subjected to. And if we don't go through this painful system, then the policies that are built around it can be attacked just on the grounds the analysis was shoddy. And that's certainly not something that we want to have happen. And so we need to hold our feet to the fire and go through this arguably painful, but it's definitely necessary effort. Have more than one hammer. I said it once, I'll probably say it again. Everything should be an agent-based model. I love agent-based modeling. I think it's the greatest thing ever. But even I am willing to concede that you don't always need an agent-based model, much as it pains me to say that. There are a ton of different tools out there. And computational social science is far, far broader than simply agent-based modeling. Again, it pains me to say that, but it's true. We talked about it already. There are gigantic data sets about, that describe social dynamics. And there's no end of interesting analyses that could be done just with those. In fact, just the Old Bailey data could be decades of research right there. Never once building a generative model, an agent-based model. And so there's lots of machine learning tools out there that are useful here. Lots of artificial intelligence, lots of agent-based models. And depending on the scale you're going after, there are cognitive models, there are game theoretic models, all of which can be used usefully and productively, depending on the scale, depending on the problem that you're trying to answer, depending on the questions that have been asked. So, this is an inherently multidisciplinary science, and you should embrace it. Go after it. You learn as many tools as you can and bring them to bear. Let 1,000 flowers bloom. Some of the analyses are going to be great. Some aren't going to go anywhere. But you won't know till you try. And this brings us to, I think, one of the most important things, and that is start simply and then stop. Just shut your cake hole. It is stunningly easy to make these things so complicated that they're hard to understand and hard to gain insight from. Right? Is that ubiquitous? A one-to-one map really isn't that useful. And so these are supposed to be models. These are supposed to be analyses. These are compressed descriptions of the system at hand, of the system in question. And, you need to embrace it. I can't tell you how many times I have built a fairly simple agent-based model, shown it to our sponsor. We've gotten some really interesting insights from it. They've gotten all excited. And then, oh, we should add this. We should add that. Oh, you didn't put this. Oh, we should put that in there too. That'd be great. And so we spend a significant chunk of time making it more and more complicated until suddenly, basically, the data that comes out is so difficult to analyze and understand, we're no longer gaining insight from it because it's hard to understand causality in the model. And then we scale it back to something that makes sense, where we have all of the important muscle movements of the system as part of the model, but we haven't added so much detail to it that it's nearly impossible to analyze and understand. And so start simply and then stop. Less is more, for the most part. especially in these social systems. These are not physical systems, remember. You know, if you're building a simulation of the parabolic flight of a projectile, you can go out, you can do experiments, you can see how well your simulation's capturing the dynamics that you're getting in the real world. Those are physical systems. And there, adding more and more detail can be useful because it can make your simulation more and more accurate and a better and better representation of the experimental evidence and data that you're getting when you're actually shooting the thing, you know, over the field. But in these social systems, that's not necessarily the case. So don't fall into that trap. And this is something that I particularly excel at, is failing early and often. You know, I've implied it a couple of times already, but I think it's worth expressing explicitly here. It is really important to not get sucked into a single way of analyzing a system, a single perspective, and a single tool. So lots of times it's difficult even to express the problem correctly the first time. So I am a huge advocate for just don't worry about trying to get all the details in there at first. Just get something going. Analyze something. Build some sort of simple model. Just build it and expect it to be wrong. Expect to fail a few times. Because that's how you learn. That's how you can start to actually figure out what the right problem is, what the right questions are, what the right data needs to contain. And so then you can actually start to make real progress. I think the key is just don't be afraid to fail, so you can just fail early and often and quickly and cheaply, so that you're not wasting a lot of time and treasure as you're figuring out what the real question is, what the real analysis needs to be. And I think this Dyson quote's particularly good. And always make new mistakes. Don't fail the same way twice. Learn from them. But, you know, embrace it. Don't be afraid to. That's, in my experience, the best way to make progress on this quickly is just to start going and fail, but just do it fast and do it cheap. Okay. And now the other thing that comes up very often with these tools is prediction. And this actually does keep me up at night periodically because the federal government deals with that a lot. They want prediction. And it's tough in this context. We want to think more about forecasting, essentially. It's likely the system will, you know, if perturbing a social system in this way is likely to produce this outcome, but it might produce one of these other five. We've seen all of them. It's just usually we get this one, and that sort of thing. And so I think it's far better to think about this as sort of weather prediction, weather forecasting. So essentially it's kind of likely to occur, unlikely to occur, whatever it is, not point prediction.